Thank you so much. So my name is Ali Tourani. I'm currently here in Luxembourg, a postdoctoral research associate at the SNT Center of the University of Luxembourg. And in this presentation, I'm going to talk about, let's say, my main project here that I started developing since 2024, if I'm not wrong. And it's called vS-Graphs, and the idea is to tightly coupling vS-LAM and 3D scene graphs, exploiting hierarchicals in understanding. With this, I'm going to start with some introduction for some people maybe who are not familiar with this concept. So we're going to talk mainly about the concept of SLAM, or simultaneous localization and mapping. And here the idea is how to do the mapping and self-localization, let's say, simultaneously using autonomous agents. So we can, in this presentation, we mainly talk about autonomous robots, but it can be also extended to autonomous vehicles as well. And so here we can think about a joint problem, like if you have a good localization, we can generate a good map of the environments surrounded by the robot. Let's say a mobile robot which going to the different parts of an unknown environment. And at the same time, so if we have a good mapping of the environment, we can, let's say, localize ourselves much better there. So when we talk about the SLAM, we can think about different sensors. So there are a wide range of different sensors mainly used in the SLAM. We can think about LiDAR, IMU, radar, but at the same time, we can also think about the cameras as the vision sensors. So again, we know that with the cameras, we can have a wide range of options. We can think about event cameras, monocular cameras, stereo cameras, RGBD, and other stuff. And with this, I'm going to talk about the visual SLAM, which is when we want to use the vision sensors in SLAM. So let's consider you have a monocular camera or an RGB camera or any kind of visual sensor. So in this case, you want to you are capturing some frames of the environment. So you pass these frames, let's say, to some pipelines for feature extraction. Here you can see that we are extracting the visual features of the frame using well-known applications such or algorithms like ORB and other stuff. But these features, they can be also matched throughout the different frames. So we can actually track them to realize how well these features are being, where is the current location of the same features in the next frame? So we are actually having the task of tracking here. And with this, so having the tracking information, we can it can actually lead us to motion and pose estimation. So we can realize what is the pose of the camera while recording this set of frames for us. And among all of these frames, so we know that, for instance, there are a lot of frames. It can be like 20, 30 frames per second. Of course, it depends on the FPS of the camera. But we don't need actually to process all of this information. So we might need to have some of them as the keyframes, which are the most, let's say, relevant for us, and also the one which contain more distinct information. So in visual SLAM, this can be mainly considered as a front end or the visual odometry part of the pipeline. At the same time, we can think about this type of visual features, and we can map them in the 3D, let's say in the 3D world, to realize what is this location of these 2D points in the image in the 3D world. And in this case, we definitely need to have the camera parameters for this. So this can lead to local mapping, and by optimizing this, let's say, this maps of this visual features mapped in the environment, we can have a let's say, updated version of these locations. On the other hand, we can think about saving this set of visual features somewhere, like as a database. And this can lead to some very useful information about loop closure, which means that, for instance, we realize that, okay, we've been in this particular location before, because this set of features are completely similar to what we have seen, let's say, for instance, 30 seconds ago. And this can also lead to bigger optimization, which can be called global optimization. So we can have all of these as a backend of this visual SLAM. So this is just like a very general ideology about the visual SLAM pipelines. So using this visual SLAM, we can have different type of representations. So what you have seen so far is the geometric maps. So the maps of the environment in which we can just show with the 3D map points or 3D point clouds. We can think about the semantic maps when we have more useful information regarding the description of the environment. So we can have some voxels or the semantic point clouds that can actually create this type of information for us. Or we can also have high-level entities or high-level representations such as scene graphs. So these scene graphs here are a set of nodes and edges. So the nodes can actually be the objects, like the semantic objects that we detect, or the landmarks in the environment. And the edges can be the topology and also like say how well they are connected to each other and what is the relation among them. So this can actually model the environment in a more structured way, and can also show also the apart from the visual and semantic information, we can also have the spatial, let's say, relationship among the objects that we detect. So here the gap that since we started working on the project was sensing was that so we have the visual SLAM that can actually create the, of course, we have some optimization things happening, and for the modeling of the environments created by the visual SLAM, in this case, we generally use some sort of graphs, which are called factor graphs. And this is always like help us to always update the relationship among the visual features that we detected so far. And this, at the other hand, I just introduced you with the scene graph. So in general, the 3D scene graphs. And the main idea here that we realized that there is something that which was lacking and there wasn't so much attention in the environment was to, let's say, couple these two type of graphs. So we want to couple the factor graphs of the visual SLAM backbone and the 3D scene graph for representation of the environment. And this should be some sort of environment modeling in which we can always optimize and we can also update it while the more visual features are being added to the reconstructed map. And for this case, we actually realized that there are some particular semantic information in the environment which can actually help us to better model the environment in which the mobile robot is functioning. And we could classify it into two different semantic levels. So the first one is the building components, that we call them building components, and the second one are structural elements. So the building components are actually lower level semantic entities for representing an environment, which is in our case for now walls and ground surfaces, but we are also currently working on the other stuff like windows and staircase and other stuff. So these are the type of semantic information that the robot can use to be more aware of what's happening in the surroundings. But let's say on the other hand, we can think about higher level semantic entities which can be extracted using this type of lower level semantic information. In this case, we thought about rooms and floors, which are, for instance, a room is a combination of walls and ground surfaces and windows all together. So this is actually very useful information that the robot can actually realize and model its surrounding environment. So the main idea comes from the LiDAR-based SLAM work that we were developing here in our group. But then we started thinking about using the vision sensor to do the same thing, because the visual sensors can also provide you with very rich semantic information as well. So this is what the output of this visual S-graph, which is this system that I'm going to talk about in more detail, would generate for you. So this is a model of the environment. Actually, it's like the office set that I'm currently working on. So you can see there are a set of rooms, or let's say offices in the environment, and all rooms can shape together floors. And of course, each of these rooms can are let's say comprised of some walls that could shape that room and could actually lead to the detection of that room. So here in the visual SLAM, we have some, let's say, some keyframes or some visual information where the pose of the camera while it was capturing this type of information was saved. At the same time, as I said, we have some keyframes which are, so apart from the frames, which are, let's say, the processing or is happening in the frame level, we can keep some of them as a keyframe. and then we pass it through this panoply segmentation pipelines to better, let's say, filter out the parts of the environment which contains the walls and ground surfaces in our world. So you can see also how well it is working. And since the keyframes are not that much, let's say, compared to the frames are not that much intense, so we can actually process them and still keep the real-time performance of the system. You can see that the walls and the grounds, let's say, planar surfaces of the environment has been detected using this panoptic segmentation pipeline. And for that, we also could extract the geometric information like the 3D equation of that plane, like the plane of a wall or the plane of the ground, and map it also in the environment. So we can think about, again, in the factor graph, we can think about these connections, which is keyframe to building component connections. In this case, for instance, a set of keyframes could lead to the detection of walls. So we keep also this type of information. And using this type of lower level semantic entity, as I said, we can detect the higher level semantic entities, which are the structural elements, including rooms and floor surfaces. So again, a room is a set of walls. So we also have this type of connection between the building component to rooms. And there is also connection between rooms to floor surfaces. So we can clearly see the patterns of the mapped 3D scene graphs and the factor graphs of the vS-LAM here. And this is how the system works. So we have, again, a robot goes to the different parts of the environment, mainly indoor environment in our case. You can see it's also compatible with any kind of robot because it's wrapped by ROS with Jazzy. And for panoptic segmentation, we can, for now, we have YOSO and PFCN, but we also recently added YOLO. So we have a wide range of options actually to work with this stuff. And for the sensor, it works with monocular cameras, but we prefer for now the RGBD because we also have the depth information and we can better model the planar surfaces, including the walls and ground surfaces in the environment. And the good point is it's also open source that I'm going to also introduce you to how to use it actually. So let's say we want to have a closer look how the system actually works. So again, we have a set of frames. We pick some of them as the keyframes. This is actually handles in the backbone of the vS-LAM pipeline. And by processing each of these frames, we have access to some let's say visual information. Let's say the 3D map points that were mentioned. In the previous versions, we also had some markers. So if there were some fiducial markers in the environment, we could actually think about it. But for now, you can skip it because it's not like that much useful in the current version. But since the slides are a bit not updated, I still also have the markers here. So using this 3D map points of the environment and this, let's say, panoptic segmentation pipelines that I showed you, we can actually first detect all the, let's say, planar surfaces in the environment. And then in the panoptic segmentation, we can realize that, okay, so this particular, let's say, plane that I detected belongs to a wall, and the other one belongs to, for instance, a ground surface. So we can also label this type of semantic information. We can have these 3D models of these building components. Again, using this in another separate thread, we are constantly looking for the detection of higher level semantic entities, including the rooms and floors. And for rooms, we think about the walls facing each other in a let's say a closed area, and this can actually lead to the detection of a free space, which is a room. And also we can also think about high level labeling, such as separation between the rooms and the corridors, which is also currently supported in vS-Graphs. In terms of the implementation, you can see this was what the baseline was looking like. So it was for the baseline, we used OrbisLAM 3, which is a very well-known vS-LAM pipeline. This is the baseline, and then we added, again, as I said in the first versions, we started to also thinking about the importance of fiducial marker if they exist in the environment. But for now, we don't actually rely on them. And then we added one thread, which is building component recognition. It takes the the keyframes, and then it passes through some semantic class filtration. And using this, we can also have the filtered semantic outputs of the scene that the robot is seeing. After that, we have this, of course, the point clouds, so we can actually downsample the amount of data, and by fitting some planes, we can actually realize what is the 3D equation of these walls and the ground surfaces that we detect, what are the equation in the word point of reference. So this particular, let's say, thread is actually mainly designed to handle the planar surfaces of the environment, in which they are all actually later semantically verified as well. So we added another thread which works completely separately from this building component recognition, and that is called structural element recognition, which always looks for this set of walls and layouts of the walls and ground surfaces to detect the higher level semantic entities, including the rooms and floors here. And these are the parts of the, let's say, like the parts that have been modified in order to better match with the pipeline of vS-Graph in the back. So then we did a wide range of evaluations. So we collected a lot of data sets. So there are some standard data sets available. We also collected some data sets, let's say some in-house data sets using our mobile robots here. Mainly in the indoor environment, so you can see the data sets like can cover a trajectory length of more than 600 meters. So it was a wide range of all different type of data sets that we use for the evaluation. And then we evaluated compared to the other well-known, let's say, RGBD visual SLAM pipelines, including the baseline, which was the VSLAM 3, Droid SLAM, Elastic Fusion, and that SLAM. And then realized that actually our system works better if we just have the building components, which is the ground and wall surfaces of the environment. But if we even go one step further and we detect also the rooms, and by tightly coupling this type of information in the SLAM backbone and also in the factor graph backbone, we realize that actually our system works much better than all these evaluated visual SLAM pipelines. And the main reason is that we are imposing more type of semantically verified information in the background. So this actually help the robot to actually have a better understanding of what's going on their surrounding. At the same time, better model the environment with the higher accuracy. We also did some mapping performance. Let's say how, in very simple words, how much information do we need to reach, let's say, a better understanding of this type of information. And for that, we realized that the system is still, by comparing against the baseline, we realized the system can do the same job as the baseline, but with the lower amount of map points of the environment. In terms of the runtime analysis, as I said, the system works in the real time with the plus 25 FPS. But of course, it depends on the hardware that you are going to use it. But for that, we definitely need the GPU for the semantic segmentation. So the tracking happens in real time. The local mapping also corresponds to the wide range of the processing time here. But the building component recognition and structural element recognition are two threads that we actually added for our work, and we realized that adding this type of stuff doesn't negatively impact the real-time performance of our system. And we also compared against other systems which somehow work the same. So like S-Graph is the main idea come from this LiDAR S-Graph, the one in the middle. And we also compared against Hydra, which is another well-known system which can create the 3D scene graphs of the environment, but this is actually not really a visual SLAM, so we cannot actually expect to directly optimize it in optimize the reconstructed 3D scene graph in the SLAM pipeline. But the one that we create, the one on the right, the visual S-Graph, we can see that we can still achieve the good representation of the environment while keeping the semantic information and the semantic modeling of the environment, apart from all the positive points about the lower trajectory errors. And you can also see that we also tested with different type of data set with different layouts. So some of the, let's say the rooms are not really so simple. It's not like a four-wall room. So they are a bit more arbitrary shaped. And with the bigger data sets, such as this SMAPper MR3, which we collected in all the offices of this building that I'm currently in. And we could actually see that the system can generate this type of information. And if you're interested to know more about this, as I said, so the paper has been accepted in RAL. We presented it in ICRA, let's say in a workshop, but the main presentation would be also in next ICRA in 27. And in terms of the source code, if you want to test it, and if you want to actually use it for your work, we can still have it with this from this address. We also have the Docker version, so we can super quickly test and use this framework. And we are currently also working to better improve the system. So we want to currently also supporting the passages. So we are including this type of information as well. And this is in another branch of the GitHub repository. You can also see that. And we are also currently working to include the staircases as well, which can lead to have a multi-floor support of the system. Apart from this, some other, let's say in parallel, we have some other projects which we also encode some prior maps, such as like beam information or building information models, which can better let's say, provide the prior information to improve the reconstruction accuracy. And this is called inform vS-Graphs. This is something which is we also let's say submitted to RAL, which is still under review. And we are also developing semantic loop closure detection so that we can actually realize, okay, I have seen in this particular room before, so now I'm in a loop of the environment, so I can trigger the big global optimization to better improve my model. And this is the ongoing parts of this project right now. And with this, I'm going to finish my presentation. Thank you so much for your time and for your attention. I'm open for any questions.